Welcome. This video is all about the concept of related rates, one of those crazy topics that you hear about in calculus that drives people nuts because they're word problems. The calculus isn't really the tough part about what we do, at least in my opinion. It's actually the setting up the problems and solving them just like any other word problems you've encountered before. So let's talk a little bit about related rates and do a couple problems together. So actually I have 6 problems ready for us to talk about with related rates so that you feel like you have a pretty good idea of how this works. I can't do every possible problem, but I'm going to give you some that'll give you a taste of what related is all about. So before we talked about the taking a derivative implicitly in a procedure that involved having to respect the x. All right. Now, as we consider a changing world, ones where things are changing as time goes on, we're going to have to respect time or respect t. Okay, so when we take our derivatives, we're going to take derivatives that sound like dy dt and dx dt. All right, that'll allow us to figure out how things are changing as time goes on. Now, the trick is to try to come up with some sort of relationship between variables that we know information about and ones that we want information about. So let's start with the simple part about this. So just taking the equations flat out. Suppose 5x plus 11y is equal to 9. And we want to find an equation that relates the rates of change of x and y with respect to time t. Well, what we say is the derivative of 5x is 5 times dx dt. All right, that's the rate of change of x with respect to time. It's just how x changes as time changes. We do the same with the 11y, and we say that derivative is 11 dy dt, and then the derivative of 9 is 0. So we found an equation based on how x and y are related that relates the rates of change. So 5 dx dt plus 11 dy dt is equal to 0. So, for example, if we knew something about dx dt, let's say that's equal to negative 4, we could find out what dy dt is when x is equal to negative 1. All we got to do is plug in negative 4 for dx dt, and then solve for dy dt like we do any other sort of algebra problem. So we move the 20 to the other side, and we get dy dt is equal to 20 divided by 11. Okay, so that's simple enough. Some common formulas that you'll see. We got the volume of a cube, s cubed. Volume of a sphere, 4/3 pi r cubed. Volume of a right circular cylinder, pi r squared h. Volume of a right circular cone, 1/3 pi r squared h. Now typically you're given these formulas as part of the information given in the problem, but they are helpful to know, and you will be seeing them quite frequently in these sort of problems. We'll also use other area formulas like the area of a rectangle or a triangle. We'll also use trig formulas, sine, cosine, tangent. And then what we're going to do also is we're going to try to hunt for similar triangles. And these similar triangles will help us to find relationships between variables. So let's start out with example number 2 here as far as word problems. A spherical balloon is being filled with air in such a way that when its radius is 2 feet, the radius is increasing of 1/6 of a foot per minute, or 2 inches per minute. How fast is the volume changing at this time? So as you do these problems, it might be helpful to underline important pieces of information, like the radius is 2 feet. The radius is increasing at the rate of 1/6 of a foot per minute. The foot per minute is a giveaway that this is a rate of change right here. And then what are we trying to find? How fast is the volume changing at this time? All right, so steps that you want to follow when you're solving these problems. Draw a picture if it helps you out. So I have a picture right here, Happy Days, the balloon. It's being filled with air. We're going to create our variables. We've got r for radius, and then we'll use v for volume. So then we need to figure out what's given and what needs to be found. Well, I told you that the radius is increasing at the rate of 1/6 of a foot per minute. So this is what we call dr dt. dr dt is 1/6 of a foot per minute. Rate of change of our radius over time. At this particular moment, now remember this balloon is like inflating, it keeps on being filled up with air, but we're saying at a snapshot, at a particular, if we were to take a picture of this balloon, at this moment the radius is 2 feet. And we want to figure out how fast is the volume changing at this time. So that would be dv dt. So then we ask ourselves, is there an equation that relates our variables, both the dv dt that we're missing and dr dt that we have? In other words, is there a way to relate r and v in a sphere? Well, in this case, volume is equal to 4/3 pi r cubed, an easy way to relate those. So now we take the derivative with respect to time. So we know v is equal to r, 4/3 pi r cubed. So then dv dt is equal to 4/3 times 3 pi r squared dr dt. All right? So I just take a derivative just like I do any other sort of derivative. So 4/3 pi r cubed, the derivative is 4 pi r squared. And we need to make sure we have a dr dt at the end because we need to respect time. So dv dt is equal to 4 pi r squared dr dt. Once we have all the information we need, I put it up here. So we got r dt is 1/6, radius is 2 feet, and we want dv dt. So I plug in, I got 4 pi times 2 feet squared, that's r, times 1/6 foot per minute, that's dr dt. And notice, by the way, I put the units in here on purpose for this problem because notice we get a feet squared times a feet per minute, which gives us our new units of feet cubed per minute. And then we multiply out all our values, and we get 4 pi times 2 over 6, which is 8 pi over 3 feet cubed per minute. That's how fast the volume is changing over time. Right, example number 3. The length of a rectangle increases by 4 centimeters per second, while the area remains constant. So you have to imagine I drew this little rectangle here. The length is getting bigger, but the area is staying the same. So what do you think that's going to do to the width? Well, in order to keep the same area, if we're lengthening the length, then the width is going to get smaller. Okay? So we want to find the rate at which the width of the rectangle changes at the moment the instant it has a length of 10 centimeters and a width of 5 centimeters. So same process. We drew a picture. We got our variables w and l. So then we ask ourselves, what's given? Well, the 4 centimeters per second is a giveaway that we have a rate right here. So we have dl, derivative of length with respect to time, is 4 centimeters per second. The area remains constant. That's kind of a hint at another thing. So if the area is constant and it's not changing, that means dA dt is 0. That should be centimeter squared per second. Sorry. And we want to find the rate at which the width changes at the moment the rectangle has length of 10 centimeters, width of 5 centimeters. So the rate we want is dw dt. So we ask ourselves, we have dl dt and we have dA dt. Can we figure out what dw dt is? So do A, L, and W all relate to each other in a rectangle? Yeah, area is equal to length times width. All right, so we take the derivative with respect to time. So A is equal to L times W, so here we're going to have to use the product rule. All right, so left d right plus right d left gives us L dw dt plus W dl dt is equal to dA dt. So this one involves a product rule here. So now we solve. Let's see what we got. So L is 10, dw dt is what we want to find, W is 5, and dl dt is equal to 4. So I put all that up here. All right. When you solve for dw dt, you get negative 2 centimeters per second. All right, so kicking it up a notch here, let's talk about other sorts of problems you might see that might involve trig. A model rocket rises vertically and is monitored with a camera from a spot 1,200 feet from the launch pad. So this rocket's going up right here off to the right. Here's our camera right here, and it's 1,200 feet horizontally from the launch pad. The camera angle changes at the rate of 0.2 radians per second to try to track the rocket. So the rocket's going up. The camera angle increases what we call an angle of elevation. How fast is the rocket rising vertically? At the moment, the rocket is 500 feet above the launch pad. So you have to imagine the rocket's still going up. So it's like if we took a picture with this camera right at the moment when the rocket's 500 feet up, what is the rate of speed of the rocket at that moment? Okay, so we drew a picture, we created the variables. 1,200 is not changing, so I'm going to put that there as 1,200. But the h, on the other hand, is something that's changing, so I'm going to give that a name. I'm going to call that h for height. Let's see what's given. All right, well, let's see. We got a rate of change, 0.2 radians per second. So that's theta's change. So d theta dt is 0.2 radians per second. At this moment, the height is 500 feet. And then what do we want to find? How fast is the rocket rising vertically? That's dh dt. So we ask ourselves, is there an equation that relates theta and h? Well, we've got h, 1,200, and theta, and those are opposite over adjacent in relation to theta, h and 1,200. So we can use tangent of theta. Tangent of theta is equal to h over 1,200. Okay, so step 4, we want to take the derivative with respect to time. So it's a little bit tricky to do tangent of theta is equal to h over 1200, so I recommend that you multiply both sides by 1200, and you get 1200 tangent of theta is equal to h. Derivative of that would be 1200 secant squared of theta, d theta dt, equals dh dt. So now we need to solve. So we got two things we need to fill in, whatever secant of theta is, and we need to fill in whatever d theta dt is. D theta dt we already know is 0.2 radians per second. So the only question is what is secant of theta? So off to the side I made a little note here. This is a 500, 1200, 1300 triangle. So if you were to solve this using Pythagorean theorem, you would get 1300 as this opposite side right here. Remember, secant of theta is hypotenuse over adjacent. So this is 13 over 1200. 1300 over 1200. So I solve. I plug in secant of theta is 1300 over 1200. I know d theta dt is 0.2, so I plug everything in and solve, and I get dh dt is 281.667 feet per second. Example 5. Sand is piled into a conical pile down below here whose height equals its diameter. Suppose the height increases at a rate of 7 inches per second. At what rate is the sand pouring into the pile when the pile is 14 inches high? So h is equal to 14 at this moment. And our diameter and our height for this particular cone, even though it's not drawn to scale, are the same. So that means that the height is the same as twice the radius, by the way. So we drew a picture, we got h and we got r. Figure out what's given. The height increases at a rate of 7 inches per second, so that's dh dt, 7 inches per second. This moment, height is 14 inches, and we know also that h is equal to 2r. How can we relate dh dt? And what we want to find, which is the rate of change the sand is pouring into the pile, we'll call that dv dt. So does volume and height relate to each other in a cone? Yes, we talked about this just a second ago. Volume equals 1/3 pi r squared h. So this one is a little tricky. I'm going to show you a different way to solve it in class, but I want to show you and emphasize something in this particular problem. And that is that volume is equal to 1/3 pi r squared h. So this is another product rule problem. Okay, if I wanted to find dv dt, well, that's 1/3 pi times the derivative of r squared times h. Well, if we do left d right plus right d left, that would be times r squared dh dt plus 2r dr dt times h, which is what we get right here. So that's all product rule. We also know height is equal to 2r, so that means that dh dt is equal to 2 dr dt. Any relationship you have between two variables, you can find their derivatives. Okay, so note, once we solve this, we know that when h is equal to 7, r is half of that, which is 7 halves. So now I can plug in 7 for r. dh dt is also 7 inches per second. I know that r is 7, and I know that our r is equal to 7 halves, and our dh dt is equal to 7. So when I plug in all my numbers here, I get 343 pi inches cubed per second. Last one. A person 6 feet tall is walking away from a light that's 10 feet high at the rate of 7 feet per second. At what rate is the length of the person's shadow increasing? So you have to imagine a person's here. As they walk away from this lamppost, their rate of change is dx dt, and then the shadow here is on the ground. That's going to be dy dt is the rate. At what rate is the distance from the tip of the shadow from the light changing? So we drew a picture and created variables. So x and y, x is the rate of change of the person, y is the shadow. So we have dx dt is equal to 7 feet per second. The person's height is 6 feet, height of the light is 10 feet. And what we want to find is what dy dt is, and then dx dt plus dy dt. That's the distance from the tip of the shadow from the light. So that's the total distance here. Okay, so how can we relate these two variables? Well, notice I got a big triangle and a small triangle. So the small triangle has 6 feet as one side. The lamppost is 10 feet. So 6 over 10 is equal to y over x plus y, the length of the big triangle. If you solve this, this means by cross multiplying we get 6x is equal to 4y. So now we take the derivative with respect to time. So 6 dx dt equals 4 dy dt. And I know dx dt was equal to 7. So when I solve for that, dy dt is 21 halves feet per second. So that's the change of the shadow. And then the shadow plus the person is the last part That's dx dt plus dy dt. You add those up, you get 35 halves feet per second. Thanks for watching.